Hi, folks. It's Dr. Sino. We'll be getting ready to go in just a few minutes. Just want to get the live stream set up before class time actually is in. So, see you all in a couple minutes. Hi there. See people starting to come in. Again, we'll get started in just a minute or two. Whew. Well, it's easy when all you guys have usernames that are exactly the same as your actual names. You'd be amazed how many people have these crazy ass usernames, so I have no idea who they are when I see them. Listen, just another minute or two, and we will get started. First off, let's do a volume check. Can you guys hear me okay? Just type in the comments if you can hear me. If you need me to up volume or something, let me know. I can up volume on the mic. Thank you very much, Nat. All right, that's that. I see we've got a number of people already here, and if people are late, I don't know what their freaking excuse is. Come on, guys, you don't have to get out of bed for this. So first off, I want to thank you for bearing with me. This has been a rough time for me, and I understand the online stuff is probably been more difficult than usual for you. This material can be a little challenging, and so I understand some of you might be having problems with it. First thing I'd say is take a deep breath. Don't worry. It's going to be okay. You're going to get this. Some of you, I haven't finished grading all the assignments, but looking at some of the assignments I've gotten already, a lot of you are doing very well on this. And so that's great. Some of you are not, and that's all right, because we're going to have a chance this class and next week when we're back in our regular time to resolve any problems you have with it. I'm going to make sure everyone is prepared for the final project. I know some of you might be scared. This is not stuff you've done before, but don't worry. We are going to get through all of this. All right. So what I want to start off by doing is giving kind of a review of the stuff we've done, or well, not really we, that you've done from the online stuff. So let's start off by talking about hypothesis testing. Well, actually, we should probably go back a little more and look at central tendency, standard deviation, all that. So first off, the first big concept you had to get was measures of central tendency. So central tendency, we've got a couple different measures, mean, median, and mode. But the one we're going to wind up using the most is the mean. Now, mean has this big scary equation. And I actually include that big scary equation for a reason, because it is a big scary equation for something that you all know how to do perfectly well. The mean, to find the mean of a data distribution, all we do is we add up all the numbers. Hi, hey, there's you too, Allison. To find the mean of a distribution, all we do is add up all the numbers in the distribution and divide by the number of things we had. So it's not hard to do. Oh, Cassandra's here, but she can't comment because she's creating her account. Do you guys not have YouTube accounts already? I mean, my God, I'm twice your age. I have a YouTube account already. Oh boy. Where do you watch music videos? Or maybe you don't watch music videos. Anyway. So we're going to use the mean most often. The mean, again, is this big scary equation, but I include the big scary equation because it isn't actually that hard to do. So the scary equation makes it look like it's hard, but it's not really that hard. Now, mean isn't the only one we're going to use. There's certain distributions where it makes more sense to use a median or a mode. So if we've got a multimodal distribution, something doesn't look like a normal curve or a normal distribution, then it makes sense perhaps to use the mode or the median instead. But for the most part, we're going to use the median. Now, the median, as we'll see, has some problems. It is very sensitive to outliers. So if you have big outliers, it can push the can push the mean one way or the other. And that's why we times will use the median, because the median isn't as sensitive to outliers. It's not being pushed around as much by the outliers. We've talked about this in terms of like the income distribution in the United States. The income distribution is important because if we just look at mean income, it looks like people are doing pretty well. But in fact, the median income in the United States is much higher than mean income. Now, why is the median higher? Why is the mean higher than the median? Because it's not a normally distributed distribution. That is, there's a lot of people who are at the middle of the distribution, sure, who have moderate levels of income, but there's also a large group of people who are really, really wealthy over here. So we can imagine your income distribution, you've got a peak over here, and then a very long, fat tail with lots of people over here that are very, very wealthy. And that's going to throw off the mean and push your mean higher, but it's not really going to change the median very much. So as a result, the median is going to be lower. The median is going to be lower than the mean, and the mean isn't going to be the best representation of what is actually going on in the distribution. Now, so we've got our measure of central tendency, our normal one is going to be the mean. And we're also going to have a measure of dispersion. So dispersion is our measure of how widely dispersed our measure is, how far away from the mean data points are. So what we're going to use for that, for the most part, is going to be standard deviation. Now, standard deviation is another one of these really scary equations, but it's actually not that hard to do. So standard deviation distribution, simple terms, is the mean distance to the mean. So for any data point in the distribution, we have to ask, how far away are we from the mean point of the distribution? So if the data on average are pretty far from the mean of the distribution, then we would say we've got a wide standard deviation. And that's going to tell us our data is going to be, well, the term we use for this is plateaukurtic, but it's going to be kind of wide, right? So you got the mean, and then it's kind of spread out kind of gently around there. If you've got a low standard deviation, all the points are really close to the mean, and so it's going to be a very narrow distribution. And so the narrow distribution is going to have a low standard deviation, and the very wide distribution is going to have a high standard deviation. Now, when we're taking our equation for standard deviation, things get a little trickier than just finding the mean distance to the mean. The problem is that if the definition of the mean is that there's an equal amount of data density above the mean and below the mean. And the problem is, therefore, if I take all the data above the mean and subtract all the data below the mean, I get nothing, because it's exactly as much above as below the mean, which is what makes it the mean. So in order to find the mean distance to the mean, remember, distance is always going to imply subtraction. What I'm going to do is subtract how far away data points over here are from the mean, and how far away data points over here are from the mean. The problem is, when I do that, it winds up being 0, because there's exactly as much data below the mean as there is above the mean, by definition. So what I have to do in order to make the standard deviation work is square the distance. Now, why do I square it? Well, I square it so that the negative values, the values below the mean, get squared, so they become positive. And so now I am doing I've got all positive values, and I'm finding all positive distances. Now that, of course, complicates things a little further. Why? Because now my standard deviation isn't the distance to the mean, it's the squared distance to the mean squared distance to the mean. And that's just nonsense. So in order to get rid of the squared, so I'm not working the square distance to the mean, what I do instead is I then take the square root. So the standard deviation is the square root of the squared distance to the mean, which sounds like it's just the distance to the mean, but it's not quite. Think about it. The problem with that is that by squaring everything, I've in fact put more weight on the things that are very far from the mean, that is the outliers. So just like when I'm taking a mean, the outliers are going to be privileged. The mean is going to take a greater count of outliers than perhaps I'd like. The standard deviation is as well. The standard deviation is going to put too much emphasis on outliers. And so if I have a lot of outliers, my standard deviation is going to be larger perhaps than I might want. Now, this has led some people to suggest that we should use an alternate measure for what our mean distance to the mean is. So I could resolve this problem, for instance, by instead of taking the standard deviation, by squaring everything, I can make everything positive by taking the absolute value of them as well. And you could do that, and it works. And it leads to a whole different branch of mathematics and statistics. So let's just not worry about it. It's called absolute value regression. It's a big pain in the ass. Sorry, turn off this light. It's distracting. All right. Sorry about that. Okay, so we've got our mean, we've got our standard deviation. And we've got both of those put together. We can also create something that's of great importance to us, and that is a z-score. So all of you have already worked with z-scores a little bit, so you know what a z-score is. A z-score is simply how many standard deviations away from the mean a given point in the data distribution is. By the way, folks, if you do have questions while I'm talking, or you want me to clarify something, please just put in the comments. I'm happy to deal with any questions that you have while we're doing this. We're going through a lot very quickly, so there might be stuff that you just didn't get the first time around. That's fine. Also, as always, I do talk quickly. My medical stuff hasn't slowed me down at all. Anyway, so we have to be able to build a z-score. Now, z-scores are very useful in that they allow us to compare apples and oranges or any other two things we want. Because all a z-score is how many standard deviations away from the mean a given point in the data distribution is. So it's a way of standardizing the data. Oh, hi, Cecilia. Good, I'm glad you were able to sign in. So it's a way of standardizing all of our data. So for any data distribution, we can express where a data point is in that distribution in terms of how many standard deviations it is away from the mean. It doesn't matter what the data distribution is. It can be your height. It can be your SAT scores. It can be your scores on the second midterm, which are actually pretty good. I haven't finished all of them yet, but they're really looking pretty good right now. So I can compare any two data points and any two data distributions. It doesn't matter what data distributions we're talking about. I can always just compare the data because all we're doing to figure out the z-score is figuring out how many standard deviations we are away from the mean. So Tabitha is asking, okay, when we're finding a z-score, how do we do it? Do we use the chart or do we use an equation? The answer is we're going to use both. So first, we have to calculate the z-score. And the calculation of z-score is pretty straightforward. Remember, z-score is just the number of standard deviations away from the mean. So all we do is figure out for my data distribution, what's the standard deviation of the data distribution? What's the mean of the data distribution? So I can use that to find the z-score for any given point. So, all right, let's take an easy one, SAT scores. So we take your two-score SAT. Two-score SAT has a mean value of 1,000 and a standard deviation of 200. Okay, pretty easy. So if you have an SAT score of 1,400 because you're a very smart person, we can figure out how many standard deviations you are for the mean. So your score is 1,400, the mean is 1,000, and the standard deviation is 200. All right, makes it pretty easy. So I take 1,400, that's your score, subtract out the mean of 1,000, and now I know that my SAT score of 1,400, that's not my SAT score, don't worry. My SAT score of 1,400 is 400 points away from the mean. I then divide by the standard deviation. In this case, the standard deviation is 200. So it'd be 400 divided by 200. Even without a calculator, I think you can probably figure out that's 2. So that would tell me my two-score SAT score of 1,400 is 2 standard deviations away from the mean. Now, that is my z-score. So my z-score for that would be 2. And note that if I had an SAT score below the mean, below 1,000, then I would have a negative z-score. So if I was, I don't know, over Drew when I had a SAT score of 800, then I would have a z-score of -1 because that'd be 200 points below the mean, or 1 standard deviation below the mean. So I've got my z-score of 2. So what I can do with that z-score, I can leave it right there. That's enough. I just want to calculate the z-score. But if I want to turn that z-score into a percentage, I use my z-score table. And you all have the z-score tables. And so what I would do is I would find 2.0 on my z-score table, and that value of 2.0 would tell me exactly how much in a normal distribution, what percentage of the data is above that 200 and what percentage of the data distribution is below that value of 2. So when I turn my value into z-score, I can then plug it into the z-score table, and that'll turn into percentages. And that's how I can compare it with anything else and turn it into a percentage. And that's going to wind up being useful in a lot of circumstances. Tabitha, does that answer your question? All right, cool. Assume it does, and you put in the comments if you need me to clarify a little more. All right, so I've got my z-score. So I've got z-scores. And what z-scores let me do is do some hypothesis testing. Why? Because I can then see if my data distribution, if my data point is significantly different from something else. And we're going to use these scores for that. We're also going to use these scores in the percentage feature later when we're talking about regressions. So let's move on and talk a little about hypothesis testing and how we're actually going to do hypotheses. So the easiest thing I want to do with hypothesis is compare means. That is to compare the means of 2 different groups to see if those means really are different. So you've got the slides. So if you want to follow along with the slides we're doing right now, this would be the hypothesis testing slides that is available in the Blackboard page if you haven't gotten that. If you haven't downloaded that already, you can be looking at that while we're talking. So if I want to compare 2 different means, what I'm going to do is I'm going to create a margin of error around those numbers. Now, margins of error are going to be based on z-scores. And it's a little tricky to figure out exactly why that would be, but think about it this way. if we're doing a survey, and let's just assume we're working with surveys because it makes our life a lot easier. If we're working with a survey, I know that I didn't talk to everybody. I talked to a sample of people. And because I didn't talk to everybody, there's always a chance I'm going to get a weird sample. We talked about this a little bit when we talked about surveys in general. So there's always a chance that I just got a weird sample. And therefore, my estimate of what's going on in the data distribution is wrong. Not because I messed up in any way, not because I did anything wrong, just because I got a weird sample. I, by pure random chance, didn't talk to people who are representative of the overall population. So what I'm going to do then is I'm going to go back and take a look at, okay, what's the odds of that happening? And if I want to be sure that I have a pretty good idea of where the actual mean of the population is, how much off could I be? And the way we're going to do that is by calculating z-scores and turn those z-scores into percentages. All right, so the easiest way we're going to do this is with what we call t-tests. So what we're going to do is we're going to create a 95% confidence interval around our mean for any data distribution. Again, we covered this in the hypothesis testing section. I'm just doing a bit of review of it now. So what I'm going to do is I'm going to create a margin of error around it. And the margin of error is going to be based on my z-score. And it's going to depend. So what I'm going to do is I'm going to find I've got my data distribution. And the data distribution, I'm going to create what I call a standard error. Now, standard error is not quite the same as a standard deviation, but it is really similar. And for all intents and purposes, it's pretty much the same thing. Now, for a dichotomous question, that is, if you're just answering yes or no to something, the standard error is going to be pretty easy to calculate. But in general, I'm just going to give you the standard error. Or if you're working in SPSS, SPSS will calculate the standard error for you. So I'm going to calculate a standard error. A standard error is like a standard deviation. It's not quite the same thing. The big difference is the standard error also takes into account what we call degrees of freedom. That is, how many things we're actually calculating. Again, you don't have to worry too much about it. All you have to know is that for any data distribution, there's going to be a standard error, which is very much like a standard deviation. So the standard is, so I'm going to calculate a standard error, and I'm going to use the standard error to calculate my margin of error. Now, the margin of error is going to depend on a couple things. Margin of error is going to depend on my standard error, and my margin of error is going to depend on how accurate I need to be. And that's where the z-scores come in. So my margin of error equation is going to be margin of error is equal to x bar, that's x with a bar on top, plus or minus the standard error times z star. Now, that sounds a lot more complicated than it needs to be, but let's go through it real quick. So I don't know. You cannot see that at all. My goodness. Okay, never mind. That's not going to work. Stupid mirrors. All right, so my margin of error is going to be x bar plus or minus my standard error times z star. So let's break that down. So x bar is just the mean. That is what the central tendency of my data distribution as calculated by the mean. We all know how to do that. We're going to be using a lot of weird terminology like x bar instead of calling something a mean. And a lot of that's just because we want to make things sound a lot more difficult than they really are. Because we get paid to do this stuff. And, you know, if people know it's that easy, they're not going to pay us nearly as much money to do it. All right, so I've got x bar. Then I've got my standard error. Again, we know how to calculate standard error. A standard error most simply is just going to be the calculation of standard deviation for an entire data distribution. You can calculate it yourself. The equations are in the lecture, or you can multiply it, or you can just calculate it through SPSS. SPSS will do that for you automatically. Finally, we've got z star. So that's a z-score. And the z star is going to depend on exactly how accurate I need to be. Now, in social science, look, we could use any number we want for z star. Do I want to be 90% certain? Do I want to be 95% certain, 99% certain, 99.999% certain? You can do whatever you want and find the z-score for it. But in social science, we're typically going to use a 95% confidence interval. Look, we're doing social science. No one's going to die if we're wrong. So we're okay with there being some possibility that we didn't get this quite right, that we made a mistake. And we typically give ourselves about a 5% chance of that. We're okay with a 5% chance that the true value is outside of our margin of error. So creating a 95% confidence interval, all I would do is go back and find my data distribution such that there is basically 2.5% on either side of my data distribution. There's 2.5% on either side of the data distribution, then I've got a total of 5% error. So if I, again, just to use a little graphic for this, I know it's backwards, but you can still get the idea. I'm 95% certain that my true value is somewhere in here. And again, you can follow along with this in the slides. 95% certain somewhere is in there. 2.5% chance over here, 2.5% chance over there. So there's a total of 5% chance that I'm outside of this realm where I think everything is. So my 95% confidence interval is going to cover from here about negative 1.96 z-score, up to here a positive 1.96 z-score, and leaving 2.5% chance on either side that I'm just not, that I've just got the wrong answer there, that I'm not doing, that my true value is outside of the margin of error. So that's going to be for 95% confidence interval, two-tailed. I'm going to allow for data on both sides of the data distribution. 2.5% chance that my estimate is too low, a 2.5% chance that my estimate is too high. Give me all told a 5% chance that my estimate is off. Now, so my z-score, if I want to be 95% certain with 2.5% chance on the other side, all I do is go to my z-score table, and again, you've got this. This is in the download stuff in the Blackboard folder. I'd go to my z-score table and look up 2.5%. Alternately, you can look up 97.5%. It works out to be the same thing, 100 minus 2.5. So I look at my 2.5% chance. My 2.5% chance is going to give me a z-score. So to look up, find 2.5% chance, it's going to be a z-score of 1.96. So if I want a 99% confidence interval, it would be 2.57. What does that mean? So if my z-score is 1.96, that means I need to take my mean and go up 1.96 standard errors or down 1.96 standard errors, and that's giving me a 95% confidence interval. If I want to be 99% certain, that is leaving 0.5% on this side, 0.5% on this side, I would start at my mean, that's my best guess of the data. I'd go up 2.57 standard errors and down 2.57 standard errors, and that would give me 99% chance that my true value in the population is inside that data distribution. So that's what my margin of error is going to be. All I'm doing is going up or down a certain number of z-scores from my mean. And again, this can be 1.96 for a 95% confidence interval and 2.57 for a 99% confidence interval. Again, folks, I'm going through a lot of stuff quickly. If there's something you're not understanding, you need to talk about it a little more, or you just don't get something. Remember, you did listen to lectures on these, but maybe you didn't get it the first time through. That's fine. Just if you got questions, just throw it over in the comment section, and I'll be happy to address them as we go through. All right, so once I know what sort of z-score, what sort of confidence I'm looking for, 95 or 99%, one-tailed or two-tailed, then I get a z-score out of it. I calculate my standard error, put that all together, and I can create a margin of error. The margin of error is going to be useful. It's going to tell me what, so if I have 95% confidence interval, my margin of error is going to tell me, all right, I'm 95% certain that my true value in the population is somewhere in this margin of error, is somewhere around there. Now, I can use that for hypothesis testing. I can use a hypothesis and I say, all right, so in the example we did in the slides in the lecture for this, we had a mean that is 57%. I thought I had 57% satisfaction among that group. And when I create a margin of error, I have a margin of error of 3.4%. Now that means that I could be I'm 95% certain the true value of the population is between 53.6% of the population satisfied up to 60.3% of the population satisfied. So I'm 95% certain the true value is somewhere between 53.6 and 60.3. So my best guess, of course, is 57%. That's the mean of my distribution. But it could be as low as 53.6, could be as high as 60.3, and I'm 95% certain that it is somewhere in there. Now, the reason this works for hypothesis testing is that I can compare it to other figures. So if I want to say, all right, the 57%, if I've got value 57%, is that really lower than 60? Because maybe the 57%, if I want to get 60% satisfaction, maybe the 57% is actually lower than 60. But maybe it's just the true value and satisfaction of the population is 60, and I just got a weird sample, so I wound up with 57. How can I tell the difference? Well, I tell the difference by actually finding that margin of error. We'll look at the margin of error, the 95% margin of error, 95% confidence interval, goes from 53.6 to 60.3. So could it be 60? Yeah. I cannot exclude with 95% confidence the possibility that the 57 they get is actually 60% of the population. It could be. It could be as high as 60.3. I also can't exclude that it's 54%, because it could be 54%. That's within my 95% confidence interval. Now, could it be 65%? Well, probably not, because 65% will be outside of my 95% confidence interval, which is running from 53.6 to 60.3. So 57% could be 60% with some random error thrown in. If I want to be really certain, what I would do is collect more data. As I get a bigger sample size, my standard error is going to go down because standard error is partially based on my sample size. So if I just collected another 300 or 400 data points, I could probably get my margin of error to be small enough that it would no longer include 60%, possibly. All right. So I can also do a t-test for the difference between two groups. That is, I can take a look at the difference between two groups and set up margins of error for each of those groups and see if they're really different. So this comes up a lot, especially in politics, if we're doing political polling. I say, does this candidate have an actual lead over another candidate? Well, it'd be pretty simple. The easiest way to do this would be create a margin of error around the two data points. Let's say I'd say Donald Trump's approval is currently at about 39%. All right, so is that 39% is actually 40, is actually 45? Does he have less approval than Hillary Clinton? Maybe Hillary Clinton is at 45% approval. So I compare that 45% and 39%, and I'm going to do about the same thing. So I'm going to do this. We've talked about this in the lecture already. You do a t-test for differences, but the logic here is basically the same. I'm going to create a figure. I'm going to create a test figure that's going to tell me whether the difference between these two groups is big enough that it couldn't just be due to random chance. All right. So that's about all I need to do with hypothesis testing. So let's move on and start talking a little about crosstabs and correlations. Again, you can follow along with the stuff we've got in the Blackboard page. You can download the crosstabs and correlations if you haven't already, and follow along with what we're doing here. So what a crosstab does is it brings two different data distributions together. And when we do analysis on crosstabs, we're going to do analysis in crosstabs in much the same way we did analysis of when we were doing content analysis. We're doing Pearson's R or anything like that. So when I'm doing content analysis, I'm going to look at is there a relationship between these two groups? That is, are the coders different based on are the coders doing things differently? And if they are, I've got a problem with my content analysis. So I'm going to do essentially the same thing when I'm looking at a crosstab. I can do some hypothesis testing on the crosstab to see if they're really different. All right. Hopefully everyone's figured out how to do the crosstabs in SPSS. It's pretty simple. Everything we do in SPSS is actually pretty simple in general. The big problem people have with it is that it's just a program you haven't used before. And so it does take a little bit of practice. I'm confident everyone can get it though. All right. So to start with the next thing we need to do is I want to take a look at scatter plots. And a scatter plot is basically the visual version of a crosstab. And lets me take a look at the relationship between two variables. And we're going to do it almost exclusively when one or both of our variables is measured at the interval or ratio value. So what we're going to do is we're going to take a look at a data distribution between two different variables to see what the relationship between these two variables looks like. So in the example we had in the lecture, we take a look at the relationship between unemployment rate and whether the president's margin in their reelection bid. So if we take a look at our data distribution, we see the incumbent party's margin of victory is going up and down there, up and down on the y-axis, and the unemployment rate's going along the x-axis. Right? Pretty easy. Now, every point on that data distribution is going to reflect one case, one data point in our distribution. And I can use this to try and figure out what the relationship between two variables is. So let's start with an easy one. Here's an easy one I like using for examples in class. In this case, what I've got is the relationship between people's ages and people's views of homosexuals. So what do we see? Well, so on this axis, we've got how much the feeling thermometer rating, we all remember feeling thermometers, that people have towards homosexuals. And on this axis, I have people's age. Now, you'll note this is not a one-to-one data point. Each of these doesn't represent data. The age represents the median value for one age group. Otherwise, it'd just be too many data points to look at and make clear. Regardless, what we see is that, all right, if your age goes up, there's not much relationship at low levels of age between your age and your view of homosexuals, right? It's all about the same for people who are relatively young. But as you get older, it falls off, right? People who are older don't like homosexuals at all. So it looks like certainly looks like there's a relationship between these two variables. That is, we could say that these two variables are correlated. That is, as one moves, the other moves as well. Now, the fact that two variables move together, correlation, does not imply causation. So it is certainly the case that as people get older, they like homosexuals less. Now, but why is that? Well, we don't think it's just like you hit your 50th birthday and you're like, boy, I just hate gay people now. I can't deal with them anymore. No. What we think instead has something to do with other factors in the way you were brought up or the social context in which you were raised, and that's affecting it. So the fact that two things move together, it's not mean that one is causing the other. We should also note that the fact that two things are correlated doesn't imply anything about the direction of the causation. We talked about this before as an internal validity problem. The fact that two variables move together doesn't mean that one is causing the other. There's three possibilities. Two variables moving together either because X is causing Y. In this case, getting older means you to like homosexuals less, or Y is causing X. People who don't like homosexuals as much get older, question mark? Like if you say I don't like gay people, then suddenly you get 30 years older? I don't know. Ultimately, there's some third factor that's causing both X and Y. Now, in this case, we can be pretty sure that dislike of homosexuals does not actually affect your age because age comes temporally prior. That is, you were born before you had any attitudes about homosexuals or anything else for that matter. And as a result, so we can be pretty sure that it is not Y causing X. It could be, but it still could be X causing Y, or it could be some Z factor that's causing both X and Y. Now, in this case, when we take a look at relationships between age and views of homosexuality, we would say that there is a negative correlation. By the way, guys, if you did come in late, don't worry about it. It's my understanding this whole live stream is preserved for days, weeks, forever. I don't know. The live stream's there, so you can always go back and watch it again. And as a reminder, again, if you do have any questions, just throw them over the comment window, and I'll be happy to address them. So in this relationship, there's a clear downward trend. Older respondents have a much more negative view of homosexuals than younger respondents do. So we'd say there's a negative correlation between age and views of homosexuals. A positive correlation would be one in which there is one goes up, X goes up, Y goes up as well. A negative correlation is X goes up, Y goes down. And a zero correlation would mean essentially a straight line, that as one goes up, as X goes up, Y doesn't seem to change at all. Now we're going to represent correlation with Pearson's coefficient, and Pearson's coefficient is R. Why do we use R instead of P? To make your life more difficult. Sorry, not sorry. So just to go over one more time, remember, if the two tend to go up together, right, positive correlation, two tend to go down together, negative correlation, the relationship just kind of goes side to side, then you've got zero correlation, or an R equals 0. Now, correlation does use mean as part of the calculation. So like anything else that uses mean as part of the calculation, it is sensitive to outliers. So you have outliers, those outliers can drive all the relationship between the two variables. So look at a strong relationship, even if it's just driven by the outliers. This is actually why we always make sure to use a scatter plot, so we can see if it is just outliers that are driving this relationship. So when we're looking at correlations, we're going to have three factors that we're going to look at in that correlation. The first is the magnitude of the correlation. How strong is the correlation? And the correlation, R, is going to value between -1 and +1. So a strong correlation is valued close to 1, absolute value, and weak correlation is a magnitude close to 0, and of course an actual 0 would be no relationship between two variables at all. The second thing that's going to characterize correlations is the direction of the correlation. Is it positive or negative? It can be a strong positive or a strong negative. A strong positive correlation is going to value close to +1. A strong negative correlation is going to value close to -1. And third, we can look at the significance of the correlation. Now, just as we think about individual variables having a mean and a standard deviation, we can think about a correlation, relationship between two variables, as having a mean and a confidence interval around a line. So if you think about confidence interval, remember, that is just like we're taking a z-score and building this confidence interval around it, this 95%. Okay, so a positive correlation between two variables, just a question here, positive correlation between two variables means that as X goes up, Y goes up as well. A negative correlation between variables means as X goes up, Y goes down. This is, by the way, I always put the dependent variable on the Y-axis and the independent variable on the X-axis because it makes it easier for us to talk about. So in our example, the x-axis, the x variable is age, and the y variable is views of homosexuals. So as age goes up, views of homosexuals goes down. So -1 would mean you've got a perfect negative correlation. So an R of -1 means that as x increases, y perfectly decreases, and it's a very strong correlation. A +1 would mean that as x increases, y also increases. Okay, so -1 is a strong negative correlation, strongest possible negative correlation. +1 is strongest possible positive correlation. And 0 means no correlation at all. So let's think about the significance of a correlation. So when we're doing a margin of error around a data point, we're kind of doing this in 2 dimensions, right? So I've got a point, and I've got this point here. This is where I'm going to. It could be as low as here, could be as high as here. It's somewhere in there. I've got 95% confidence interval. I'm 95% sure the true value of the population is somewhere in that range. And that's what we call our margin of error, or a confidence interval. Now, I can also do this with what we call a line of best fit. Now, what is a line of best fit? The idea is that I can draw a line that best describes the relationship between 2 variables. Now, there's always going to be a line for our purposes. It doesn't actually have to be, it can be a curve, but that gets real nasty. The math gets real nasty real quick because we do curves, we're doing calculus. I'm guessing you guys don't like calculus that much. If you like it, you probably don't want to do it right now, and hell, I don't want to explain it to you right now, so let's just stick with lines. So if I've got a relationship between variables, I've got a crosstab, we can draw an imaginary line between the 2 variables that represents the relationship between those variables. So I can draw an imaginary line. We're going to call that the line of best fit. So that line is going to represent the line that best states the relationship between 2 variables. So right here, I've got my relationship. This is, again, my relationship between age and view of homosexuals. So we can see as you get older, we've got a negative correlation, it goes down. So that bold line is my relationship between the 2 variables. Okay? So that's the line of best fit. Now, does that perfectly describe what's going on in the relationship? No, it doesn't. Why? Because there's lots of data that doesn't fall on that line. Lots of data that's above it or below it. That's simply the line that is best describing it. Now, how do we calculate that line? Well, the answer is we've got computers do that for us. This is literally why computers were invented. It requires some calculus, but the logic of it is pretty simple. This line exists. The line of best fit is what it does is it minimizes the mean squared distance to the line. So it's the line such that there is exactly as much data density above the line as there's below that line. So it's kind of like a moving mean through the data distribution. And it's calculated much the same way as the mean, which again is going to mean, boy, that sentence didn't work. It's calculated much the same way as the mean, in that it is still going to be very sensitive to outliers. Now, because I've got a mean, and I can calculate a standard deviation or standard error. How? Well, it's pretty simple. I've got my line of best fit, and I've got data points that aren't on it. So I can ask, well, all right, on average, how far are data points from that line of best fit? How far away are they? The farther they are away, the bigger the standard error of my data distribution is. So for my data distribution, for my line of best fit, for my correlation, I can put together a mean squared distance to mean, y squared, same way as we did when we were talking about means. We square it in order to get rid of the negative values. So I've got my mean distance to my line of best fit, which is essentially a mean distance to mean. If that sounds like a standard deviation, it's for a reason. And this is going to be the standard error of my relationship, standard error of the relationship between these 2 variables. So if I've got a mean, the line of best fit, I've got the equivalent of standard deviation, then I can calculate a margin of error. Remember, a margin of error is going to be calculated with just a standard error, a mean, and a z-score. In this case, z-star, I want to find out exactly how, z-score, I want to find out how many standard errors away from the mean things are. I can do it. So if I've got all these figures, and again, you're not going to calculate this yourself, SPSS is going to calculate this for you. You can calculate a margin of error around your line of best fit. So just to give you an idea what that looks like, again, let's go back here. You can see I've got my line of best fit. That's the bolded line, and I've got a confidence interval around that. It can be positive or it can be negative. So it could be some part above or some part below. What those lines are telling me is I'm 95% certain that the true relationship between two variables is the line of best fit says this is my best guess. But I'm 95% certain it could be as high as that, or relationship could be as low as that. I don't know where exactly in there it is. My best guess is that line of best fit, but it could be anywhere in that data distribution. All right, so this means I can calculate whether there really is a relationship here or not. And to do that, what I'm going to do is I'm going to rely on the fact that an R of 0 means there's no relationship whatsoever. So an R of 0, remember, a correlation of 0 means that there's essentially a flat line. So a flat line means that as x increases, y doesn't change at all, right? Y just stays flat as x is going up and down. So there's no relation between two variables at all. The variables are entirely uncorrelated. So that's going to be what we call our null hypothesis when we're looking at these lines. So remember a few minutes ago, we took a look at the relationship between unemployment and president's reelection prospects. So there's a weak negative relationship here. Because if you look at the line of best fit, remember the bolded line, you'll see it's weak and negative. As you move across, it moves down. So I've got a weak negative correlation. But is it really a negative correlation? Well, to figure it out, I can take a look at my margin of error around my line of best fit. So to do that, I would figure out the mean distance to my line of best fit. So you see, there's lots of outliers up here, down here. There's lots of stuff that's not very close to the line, and that tells me there's going to be a very large standard error attached to that relationship. And so when I have a large standard error and I plug that into my equation for a margin of error, remember, margin of error is just going to be x bar, in this case that's my line of best fit, plus or minus standard error times z star. So for a given z star, given 95% confidence interval, for instance, a larger standard error is going to mean I have a larger margin of error around my line, a larger confidence interval around my line. Now in this case, the confidence around the line is big enough that even though the line of best fit is negative, take a look at this line up here, the top of my 95% confidence interval. That line is flat. What does that mean? Because that line is flat, it means I cannot be 95% certain that there actually is a negative relation between two figures. Yes, it could. My best guess is there's a negative correlation. It could be even a pretty strong negative correlation if I'm at the bottom here within my 95% confidence interval. It also could be, if I'm at the top of it, no relationship whatsoever. That it's possible that the R, the correlation of two variables, is actually 0. 0 is within my 95% confidence interval. So what does that mean? That means I cannot be 95% certain that there actually is a relationship between two variables. In the actual population, maybe there isn't a relationship. And so I cannot say with any real certainty that there's a relationship between the two variables. Now, if I had a smaller confidence interval, if I only want to be 90% confident, then that'd probably be okay. I could probably create a confidence interval such that 0 is not within my 9% confidence interval. Sorry, just getting rid of the natural light. So 9% confidence interval, I might be okay. 95% I'm not. 99% I certainly would not be, because as I get more confident in 99% confidence interval, I would have to get a larger and larger margin of error or confidence interval around my line. On the other hand, if we look at our relation between views of homosexuals and age, we can be 95% confident that line of best fit does not include 0. And because it doesn't include 0, we're pretty sure that relationship is real, that there is some relationship there, that there's less than that the true relationship population, I'm 95% certain, includes that sort of negative relationship. All right. Do we understand how this is working so far with lines of best fit and all that? If you don't understand this, tell me now. We can go over a bit of it again, because this is going to wind up being really important when we move on to the next step. We have to stop because we're about to get out of the reviewing part and get into the new bits that we're going to talk about today. All right. Well, if you do have comments, something you want me to go over again, then let's just put it over in the comment section, and I will take a look. All right. So let's move on and talk about how we're going to interpret what we're going to do with these lines of best fit. So we already have some idea of what this is. That is, I create a line of best fit that's going to represent the relationship between these two variables. And that line of best fit is also going to represent my correlation between the two variables. that is positive or negative. It can be strong or weak, and it can be significant or non-significant. Now, when I'm taking a look at these, I'm also going to be able to use this line of best fit for other things. That is, I can use this line of best fit to represent the relationship between two variables. And when I do that, that's what we call linear regression. Now, linear regression, let's start off with the most simple version of it, this univariate regression. Univariate meaning one variable. That is one x and one y. Whenever we're doing regression, we're always going to have one y or one dependent variable, but we're often going to have multiple independent variables. So linear regression is based on many of the same techniques as correlation, but allows for much greater flexibility and allows you to put in other variables. Now, the basis for linear regression is the line of best fit. By the way, if you go to your Blackboard page, you can download the content in the course document section, chapter 13 slides, as we're going over right now. So the basis for any regression is the line of best fits, and this is the line that best represents the linear relationship between the two variables being analyzed. We already know how to do that. Essentially, we're minimizing the squared distance between all the data points and the line of best fit. So calculating the line of best fit is tough, especially for multiple independent variables, but computers can do it. Scholar calculus, that's why computers were created. Now, to understand these lines, interpret these lines of best fit, we're going to go back and do some 6th grade math. I know, 6th grade math, trust me, you actually all learned this in 6th grade. And that is the equation of a line. Now, in middle school, you learned that for any value of x, and for x is always the independent variable, y, the dependent variable, is y equals mx plus b. We all know this one. Y, the value of the dependent variable at any given point in the data distribution, is equal to m, the slope. Remember, slope is rise over run, times x, so how far you are on the x, times the slope, plus b, the y-intercept, where you start off with. So x is the independent variable, y is the dependent variable, m is the slope of the line, and b is the point at which the line hits the y-axis. Hoping we all remember this. This is pretty simple. And because it's simple, no one's going to pay us good money to do it. So we need to gussy this up a little bit. How do we gussy it up? We're going to throw in some Greek letters. So to make it look more complex, we're going to take that y, and we're going to, instead of using just a value of y, we're going to turn it into y hat. Now, what is y hat? Y hat is the expected value of y. Now, we understand in a real distribution, unlike the ones you had in middle school, in real distribution, we've got error. That is, not everything falls directly on that line of best fit. Because it's not falling directly on the line of best fit, there's going to be points above it and below it. So I don't know exactly where that point is, but I know my line of best fit is. So this is my expected value of y, or in our case, y with a little hat on it. A little top half of the triangle goes on top of that. Instead of m is the slope. We're not going to use m, we're going to use a beta. So it's a capital beta. And because I'm going to have multiple potential independent variables, I'm going to call my first one beta 1, beta subscript 1. And x, well, we can't do much with x. So let's just keep it as x. So x, but I'm going to be able to have multiple ones. So instead of just x, I'll call it x1, x sub 1. And then instead of b, that is where the y-intercept is, I'm going to call it c. That is my constant, what I'm adding to all of it. So my early middle school equation of y equals mx plus b becomes an equation of y hat equals beta 1 x1 plus c. Now, that looks a lot more difficult. You've got variables with hats on them. You've got Greek letters in there. It looks awful. It looks terrifying. But, and this is important, it is the same damn equation. Y hat equals beta 1 x1 plus c is the same thing as y equals mx plus b. We just made it look a little fancier in order to trick people into giving us money for doing it. So outside the difference in terminology, the equations y equals mx plus b and y hat equals beta 1 x1 plus c work exactly the same way. That is the slope of the line. That is, for every 1 unit increase in x, y is expected to change by whatever the slope is. So if the slope is negative, then y is going to go down. If the slope is positive, y is going to go up. And the equation is going to work the exact same way. The slope is just going to be rise over run. That is, how many points up or down does y move for a 1 point increase in x? And of course, it works both ways. So if x goes up by 1, y goes up by beta. If x goes down by 1, y goes down by beta. And this makes life a lot easier, so you can move both ways. If x goes up by 2, y goes up by 2 times beta. So it all works pretty well, and with a lot of these things, it's going to help to draw a picture. If you see a picture, all this is going to make a lot more sense. Now, we can also expand out our equation. Remember, we said we've got beta 1 x1, but we can have multiple ones. So we can have y hat equals beta 1 x1 plus beta 2 x2 plus beta 3 x3 all the way up to beta k xk. And then, of course, at the end, we're still going to have just one c, or one constant we're adding into it. So if I get that big, nasty equation, y hat equals beta 1 x1 plus beta 2 x2 plus up until beta k xk plus c, that looks like a big, nasty equation. It looks hard, but it's actually not difficult. It is exactly the same thing you were doing in middle school. So when we're running univariate regressions in SPSS, it's going to be pretty simple. We just go analyze regression linear, put in your independent variable, put in your dependent variable from the list of variables. When you do that, we're going to get 3 different outputs in your output screen from SPSS. Now, of those 3, one of them is called your summary, is utterly useless. You can just delete it from the start. But the 2 other ones are actually going to matter. The 2 other ones are going to be pretty useful. So the first one we're going to take a look at is going to be our model summary. And our model summary is going to give us a couple things we're going to run into later. I know this is backwards. You can find it in your sheet, though. And it's going to tell us, most importantly, the r squared. In this case, my r squared, if you look, is 0.36 right there. Now, what the r squared tells me is what percentage of the variance in the independent variable, what percentage variance in the dependent variable is explained by the independent variables in this model. So in this case, I've got one independent variable. All I've done in this case, I've taken a look at how people feel about homosexuals, their feeling thermometer, and I've modeled as a result of age. So my independent variable is age. My dependent variable is how people feel about homosexuals. And my r squared is telling me that 3.6% of all of the variance in how people view homosexuals is caused by their age. Now, what does that mean? That means if 3.6 is explained by your age, that means that 96.4% is explained by something else, or by nothing at all. It's just random chance. Some people like homosexuals more than others, just randomly. So 96.4% is explained by other variables, or is explained by random chance. 3.6% is explained just by your age. Now, also on that, you're going to, in the same screen, you're going to have the adjusted r squared. So the adjusted r squared in this case is exactly the same. So if we look at your r squared of 3.6%, right, next to it is the adjusted r squared, which in this case is also 3.6%. The reason they're both the same in this case is because I only have one independent variable. What adjusted r squared does is it accounts for the fact that you can always goose up your r squared, you can get a higher r squared just by adding more variables. So what adjusted r squared does, it assesses a penalty to your r squared for each variable you add in. So if your adjusted r squared is much lower than your r squared, that's something you have a lot of variables in your model that aren't really doing anything. You should probably get rid of some of them. In this case, we only have one variable, so the adjusted r squared and the r squared are exactly the same. So r squared is going to come up a lot. That's what's called your coefficient of determination. And it tells you what percentage of variance in the dependent variable is explained by all the independent variables you've used in your model. So if you have a high r squared, remember, is a percentage. So r squared, a high r squared, something 0.8, 0.9, would mean you've explained almost everything going on in your dependent variables. And a low r squared means you haven't explained very much at all. There's still a lot of random stuff built in there. Now, in social science, you're never going to get a super high r squared. If you get an r squared of 0.9, it generally means you screwed up somehow. That when your independent variables basically include your dependent variable, and you're not really doing anything good. We're typically going to look for an r squared of somewhere around 5% on the low end, maybe 20% on the high end. You're not going to find much more than that because humans do a lot of weird stuff. We don't know why. So there's going to be a lot of random error built in there, and your r squared is necessarily going to be relatively low. Now, the screen we're going to pay the most attention to when we're doing when we're taking a look at our regression results is actually going to be about the coefficients. So for each variable, it's going to give me a coefficient screen. Again, you can follow along, so I know this is backwards. So I've got my first variable here. Each variable is represented by one row going across. So my variable is going to be age. And the first thing it's going to tell me is the beta that's right here. Now that beta is the slope of the line. In this case, telling me that beta is negative 0.314. What does that mean? Well, that means that on average, I expect for a 1 point increase in the independent variable, that is age, my dependent variable, that is views of homosexuals, is going to go down by 0.314 points. So, just to review, the beta is the slope of the line that best represents the relationship between my IV and my DV. So it's the M in your middle school equation. It's the beta in our equation. So my beta in this case is negative 0.314. So that means I've got a negative correlation. So as my age goes up, my view of homosexuals goes down. How much does it go down? Well, a 1 point increase in my age is expected to lead to a 3.314 point decrease in my feeling thermometer rating of homosexuals. So if you go up, so people who are 1 year older are going to be on average 0.314 points lower on their view of homosexuals. People who are 10 years older are going to be on 10 times 3.4 or 3.14 points lower. People who are 20 years older are going to be on average 6 points or 6.28 points lower on their view of homosexuals. So my beta is 0.314, and that's representing basically that slope, that line. Now, of course, we've got that line. We also have a standard error associated with that line because not everything's following on that line. There's going to be data points that just aren't on there. So there's going to be points above and below that, and that allows me to calculate a standard error. And the next thing my data might give me is the standard error. In this case, if you take a look over here, I've got my standard error. My standard error in this case is 0.36, 0.036. So what does that mean? Well, we can think of it about the same way we think of a normal standard error or standard deviation. So say on average, your data points are about 0.036 points off of that line, off that relationship. Now, what does that mean? Well, we're going to come back to that later, but remember we know about z-scores and standard errors. That is, if I use my standard error and my beta, that's essentially like having a x-bar, a mean, in a standard deviation. And I can calculate a z-score around that. And that's exactly what we're going to do a little later. The next column, when we take a look at this, my output is my standardized coefficient. Do not look at that. Do not pay attention to it. Pretend it doesn't exist. Kill it. Kill it with fire. Don't. It's a terrible thing. I don't even know why they include it. They shouldn't be there. It's just misleading. We go over one more. We're at the t-score. Now, all the t-score is my beta divided by my standard error. There's a t is essentially like a z-score. Remember, z-score is how many standard deviations away you are from the mean. A t-score is how many standard errors my beta is away from 0. So my beta divided by my standard error gives me my t-score. In this case, negative 8.729. That is, my beta is 8.729 standard errors away from 0. Now, why does that matter? Well, remember, 0 is an important number for our correlations because the correlation of 0 means there's no relationship at all. So if my beta is 0, there's no relationship. Now, I also have to build a 95% confidence interval. So if my beta is 1.96 standard errors away from 0, I can be confident that it's not actually 0. So my t-score is just beta divided by standard error. That gives me my t, in this case, negative 8.729. Now, the fact that it's negative doesn't matter for purposes of significance. It just means it's a negative correlation. The beta is negative. If beta was positive, it'd be a positive correlation. So we're using this to assess the significance of relationship between two variables. We ignore the sign. Signs simply don't matter. The final column we have to deal with in our output is over here, is the significance column. And significance here is 0, 0, 0. That doesn't look good, right? But 0, 0, 0 actually means that what we've got is a relationship that is far away, that the beta is many standard errors away from 0. And so therefore I can exclude the possibility that the true value of that relationship is in fact 0. The smaller my significance value is, the more confident I can be that there's a real relationship between these two variables. All right. We also can look at the constant. So if you look at your regression output again, you see the constant in this case is 64.411. Again, that's just the thing we're adding to all of it. Don't worry about this right now, but it'll come in handy a little bit later. So we've got all these different numbers. We've got my beta, for a relationship between two variables. I've got a standard error, I've got t, I've got significance, and there's also standardized coefficient. Don't pay attention to it, kill it with fire. So I want to find out now if there's a statistically significant relationship between my two variables. How can I do it? That is, I know there's this line. I know the slope of that line. In this case, my beta is negative 0.314. So I know I've got a slope of a line. But is that slope statistically significantly different than 0? Could that just be 0 with some random error built in, like in the previous example we had with the relationship between unemployment and president's reelection bid? Right? Remember, I have a relationship here that looks like it's negative, but turns out the relationship that 0 is in the 95% confidence interval, so it's not really a statistically significant relationship. So how can I tell the difference? Well, the same way we did there. That is, I'm going to take a look and see if my 95% confidence interval around my line includes 0. So how do I do it? Well, it's pretty simple. I've got 3 ways to figure out if it's significant or not, just based on those coefficients, based on the output I get. So, first way I can do it. Now, I know to be significant, my beta has to be at 95% confidence. I know a magic z-score for 95% significance, two-tailed, is 1.96. So, if my beta is 1.96 times as big as my standard error, then I've got a significant relationship. Now we can round here a little bit. So if beta is twice as big as my standard error, that's pretty close to 1.96, right? So if beta is twice as big as my standard error, I'm pretty confident I've got a significant relationship. So I take my beta, divide by my standard error. So in this case, my beta is negative 0.314. My standard error is 0.036. So if I take my standard error and double it, 0.036, double it, I've got 0.072. Well, 0.072, that's still way smaller than my beta. My beta is 0.314. So I know my beta is more than twice as big as my standard error, so therefore I know I've got a statistically significant relationship. So that's way number 1. Just divide the beta by the standard error. If the beta is twice as big as the standard error, then congratulations, your relationship between two variables is significant. All right, way number 2. Take a look at my t-value. Now, t-value, if you remember, is just beta divided by standard error, what I did in the last little bit. So my beta divided by my standard error. Now, what's my critical value for that? Well, again, if I've got 95%, if I want to be 95% confidence with a two-tailed test, all I have to do is see, okay, my critical value is 1.96. So is my t greater than 1.96, or if it's negative, less than negative 1.96? So if my t-value is outside the realm of negative 1.96 to positive 1.96, then I can be 95% confident that my relationship is statistically significant. In this case, my t-value is negative 8.7. Is that outside that realm of negative 1.96 to positive 1.96? Yeah, very much so. So I can be confident that my relationship is significant because the t-value has an absolute value greater than 1.96. All right, so that's way number 2. Way number 1, see if beta is twice as big as standard error. Way number 2, see if the t-value, again, for 95% confidence, two-tailed, see if my t-value is greater than 1.96, the absolute value of it. Finally, I look at my significance column. My significance column, if I want to have a t-value, two-tailed, 1.96, for my significance value, all the significance does is it takes that t-score and plugs it into what is essentially a z-score table. Pretty easy. So my critical value has to be 1.96 to get me to a 5% chance, 0.005. I'm sorry, 0.05. So if I want to see if my value is significant or not, all I have to do is look at my significance value and see, is it less than 0.05? If it's less than 0.05, it's significant. Now, all 3 of these ways are always going to give you the same result because they're all doing the same thing. Remember, the beta divided by the standard error is the t. So if my beta is twice as big as the standard error, then my t is necessarily bigger than 2. So I've got a significant result. If my t is bigger than my t, I take that and plug it into my t-score table, which is the same as z-score table, and I get a significance. So all 3 of these things, the standard error relative to the beta, the t-value, and the significance are all measuring the same thing, just in slightly different ways. So they're all going to give us the same results. In this case, all three of them are telling us that we have a significant relationship between age and these homosexuals. Now, in this case, we have a relationship, we have a t-value that is negative 8.7. My critical value is only 1.96, so that's huge. And it's tempting to say we have a strongly significant relationship. This is a really strong relationship. But we actually can't say that. We can't say it because significance is dichotomous. Either something is significant or not significant. We don't worry about being strongly or weakly or whatever significant. Significant is significant is significant. A significant relationship, we can't really go beyond that. So significance, just answering Liam's question, Liam asks, so significance just means within 95% confidence. Not quite. So if we are doing, so significance can change depending on what sort of confidence interval we're looking for. In general, we're looking for a 95% confidence interval, but I can also look for 99, I can look for 90. And significance actually means the opposite of that. So it means it's outside of that 95% confidence interval. So if a relationship between two variables is significant, that means that 0, that is no relationship, that flat line, is outside of my 95% confidence interval. So what I do to determine something significant is I build a 95% confidence interval, if I want to be 95% sure. I build a 95% confidence interval, and I see if 0 is in that 95% confidence interval or not. If 0 is outside of my 95% confidence interval, I know I've got a statistically significant relationship. Okay, let me know if that makes sense. So all these ways of determining significance are just ways of determining whether 0 is within that 95% confidence interval or not. So that's what the significance test tells me, that's what the t tells me, and that's what the beta relative to the standard error is going to tell me. Now, so we understand this case is a significant relationship. We've got 3 different ways of doing it, and of course I'll ask you to do all of those. So in practice, you can use whichever one of those 3 tests works best for you, because they're all going to tell you the same thing. Personally, I'm only going to pay attention mostly to the t-test. Just see if the absolute value of the t-test is 1.96 or not. It's 1.96, congratulations, significant at the 95% confidence interval. So I can also use this, in addition to figuring out whether a relationship is significant or not, I can use this to create expected values. Now, if you remember our equation for expected values, for one variable, pretty simple, y hat equals beta 1 x1 plus c. Okay, remember beta is just the same thing when you're in middle school, you're doing m, x is just x, and c is just b. So y hat, the expected value of y at any given point in this relationship is equal to beta, the slope of the relationship, times x, how far we are on the x-axis, plus c. Okay, pretty simple. We've got from our regression output everything we need for that. So in this case, x1 is age. The x variable is age, so I'm going to do, I've got my slope, beta 1. If you remember, if you take a look at your output, the beta is, ta-da, negative 0.314. So I'm going to take y hat is going to be equal to negative 0.0314 times x, which is the age, plus the constant. The constant also was on regression output. It was 64.4. So if I want to figure out what someone's expected value of feelings among homosexuals is for any given value of their age, I just plug in this equation right here. So y hat is equal negative 0.314 times age, x, in this case I have x sub age, plus 64.41. Now, what's the point of doing this? Well, again, I can figure out, so if I plug your age into x right here, I can figure out how you should feel homosexuals based purely on that. Now, it's not going to explain everything. We know that explains only about 3.6%, but it gives me the expected value. So if I say I can take any age and plug it in there. So if I say, all right, I want to find out what a 20-year-old would feel about homosexuals, the expected value of view of homosexual for a 20-year-old, all I would do is plug in 20 to where that says x right there. So 0.314 times 20, 0.314 times 20, let's see, 0.628 times 10, 6.28, so negative 6.28 plus 64. So negative 6.28, I would expect a value of about 58. So I expect all else being equal, that someone who is 20 years old would have an expected value of about 58. And as they get older, it would go down. All right, so I can use that to calculate expected values. So calculating expected values, it'll be harder when we get more variables, but the principle is essentially the same. The big issue is we have to know a value for every x and make sure to add the constant in, and we're good. Now, where did I get that 20 from that? Sources ask, my. You can just make up. I know in my data distribution, values of age go between 17 and 90, so I can look at any age distribution in there. Now, if I want to be more systematic about it, what I would typically do is look at the mean value of age. The mean value of age in this distribution is 46. So say, how does a 46-year-old feel? And then I might go one standard deviation up and one standard deviation down. So I say, okay, a standard deviation change in age leads to this much of a change in people's views of homosexuals. All right, so we can also, so significance is determined by 95%, we've got 95, 90, 99, whatever we're doing for our confidence interval, how confident we need to be. We can also take a look, we can also use one-tailed versus two-tailed tests. We talked about this, covered this in one of the activities we did online, but in a two-tailed hypothesis, remember, is always going to be about whether or not 0 is in there. So when I'm ever doing a regression, my big question I have to ask is, all right, is 0 in my 95% confidence interval? So for a two-tailed hypothesis, in this case, if I'm writing out, would be pretty simple. It would look just like that. Right? Hypothesis 1 is that the beta for age is not equal to 0. And it creates a null hypothesis. Remember, whenever you create an alternate hypothesis, you automatically create a null hypothesis as well. Null hypothesis will be everything that's not included in the alternate hypothesis. So the alternate hypothesis would be that it does equal 0. So I've got my hypothesis. My null hypothesis is that my beta is not equal to 0. How am I going to test that? Well, we've already talked about a bunch of ways. So I could take a look at my beta divided by my standard error. I took a look at my t-value. I took a look at my significance value. They're all going to tell me about the same thing. Now, I can also make use of a one-tailed test. So a two-tailed test, if you remember, means I've got 2.5% on either side of the distribution. And 2.5% on either side of the distribution means 95% chance left in the middle. So here's our table for that, right? 2.5% chance on this side that my mean is too low, 2.5% chance on this side my mean is too high, 95% chance left in the middle creates my 95% confidence interval. These lines, of course, are right about negative 1.96 and positive 1.96. Now, the lines in the middle are too close, it might be due to random chance. So those are close to 0. So if I get a beta that's in the middle, right, it's not far enough away, then it could be 0. And I can't exclude the possibility that it is 0. Now, that's for a two-tailed test. I can also build what we call a one-tailed test. And a one-tailed test means, for 95% confidence, which we're only using, that instead of having a two-tailed test, where we have 2.5% either side, I can put all 5% of my 5% chance of my error on just one side of the data distribution. So it would look something like this. So instead of having 2.5% on either side, I have 5% chance on this side. Cassandra's asking, will a chance to go over this in the lab? Yes, we will. Doing this in SPSS is pretty easy, but we'll go over this in the lab as well. All right, so in a one-tailed test, I put all 5% of my error on one side of the distribution. Now, so there's no error on this side, but this gives me a lower critical value. With the two-tailed test, my critical value is going to be 1.96. If I've got a one-tailed test, I've got lower, because now instead of having 2.5% on this side, I've got 5% on this side. So it pushes this line over a little farther. How much does it go? Well, so if I've got 95% confidence interval in a one-tailed test, my critical value is going to be 1.65 rather than being 1.96. Now, you might ask, all right, wait, a critical value of 1.65. That seems much easier. I'd be more likely to reject my null hypothesis because I've got a lower critical value. So if one-tailed tests give me a lower critical value, why the hell would anyone ever use a two-tailed test where it's going to be harder for you to get a significant result because it's 1.96? Well, the answer is that people don't always know which direction it's going to come out on. So in a two-tailed test 1.96 with a 1.96 critical value, It could be positive or it could be negative, and I don't know which one. And I'll accept a significant result on either side. All I care about is that it's not 0. However, if I use a one-tailed test, there's always a possibility I'll get a significant result that's just in the wrong direction, and therefore winds up being not significant at all. So if I had hypothesized, for instance, that in our our study of the relationship between age and views of homosexuals, if I hypothesize a one-tailed positive test, said I think as people get older, they like homosexuals more because they get more tolerant and they don't care about having sex with people anyway, so whatever. If I hypothesize that and I got my t-value of negative 8.729, I would say, well, it's not a significant result. As a result, because it is in the wrong direction. I hypothesized a positive result and I got a negative one, so therefore that one doesn't count. Now, this is the big reason why we have to make sure to switch or to set our one-tailed or two-tailed at the start. Why? Well, imagine that I create a one-tailed positive, and then I get actually a negative result. What happens there? Well, all right, so imagine I have a one-tailed positive result. I go one-tailed positive result, and one-tailed positive hypothesis, so I'm willing to set any value down to 1.65 over here. And then I get a negative result. I got a negative 8.729. So I got a value way over here. And I go, oh, shit. So I guess I'm just going to change my hypothesis and say, oh, I meant two-tailed, or I meant one-tailed negative. So if I say I meant two-tailed, and I just change it after the fact, then my math is going to be wrong. Why? Well, think about it. I would have accepted a 5% chance on this side. And now I'm changing to two-tailed, so I would have accepted 2.5% chance on this side. So I no longer have a 95% confidence interval. Right? I would have accepted 5% on this side, but I also would have accepted 2.5% on this side. So instead of having 95% confidence, I got 5% error on this side and 2.5% error on this side. Actually, a 7.5% chance, 7.5% error. So I no longer have a 95% confidence interval. If I change my mind about my hypothesis after running the analysis, my math is actually wrong. The math gods come and punish you, and your stuff is actually wrong. Now, we've got our univariate analysis, and univariate regression analysis is pretty straightforward. Just to review again real quick, you plug in your IV, you plug in your DV, and it's going to give you a table that looks like that, right? And in that table, it's going to be my beta, my standard error. It's going to tell me everything I need to know to determine what the relation between variables is, create expected values, and determine the significance of the relationship. Now, the problem with this is that there's always the possibility that other things are actually driving this relationship. So we talked about this in terms of internal validity problems. Yeah, it certainly looks like age is the thing that is driving the relationship between views of homosexuals. Age is driving down your view of homosexuals. But there could be other things as well. There's essentially, I could have a problem with content validity. I've missed on some things that are actually driving it. So, for instance, I know that people who hold politically conservative beliefs also have more negative views of homosexuals. And I know that people who are older have more politically conservative beliefs. So, is it really that people who are older have more negative views of homosexuals? Or maybe it's that people who are politically conservative have more negative views of homosexuals. And it just looks like it's age that's driving it because older people are more likely to have politically conservative beliefs. So, if I'm interested in the effect of age on a view of homosexuals, I might include other variables. So I might include political conservatism as a variable in my model as well. And at that point, we've moved out of the realm of univariate regression, where we're just doing one at a time, and into the realm of multivariate regression. I'm going to use multiple variables at the same time. And this is going to be one of the most powerful tools we have in statistical analysis. And we're going to get to that in about 5 minutes. I want to take a 5-minute break. It's currently 9:48. I'll be back in 5 minutes, and we'll get back started with multivariate regression after that. Thanks. If you have any questions as you're going through this in 5 minutes, put them over the chat window, and I will deal with them when we get back. All right, see you in 5. Go back in. All right. Okay, Taya, welcome aboard. All right, so I guess let's get started again. All right, so we already talked about univariate regression analysis. That is when we're taking one independent variable against one dependent variable. But we can actually do things a lot more powerful than that. We can do multivariate. In multivariate, we're going to use one dependent variable still, but multiple independent variables. Now, the idea here is that we know that things have many causes. We know the social phenomena are complex. So in this case, our example is about people's views on homosexuals. Well, it could be that age is driving it, but it could also be political conservatism. Hell, it could be the gender of the people doing it. We know that men, for instance, generally have more negative views on homosexuals than women do. So there's lots of different things that could be causing this. Sorry, just adjusting the blinds again. All right. So there's lots of different things that could be causing this, and we want to control for all of those. Allison's asking, we'll get our final next week. The answer is yes. I will give you the final next week, though you'll have plenty of time to work on it. So there's lots of potential causes for the independent variable, and so we want, for the dependent variables, we want to include multiple independent variables in our model. So to do that, we're going to do it in SPSS, exact same we did for univariate. That is, analyze regression linear, and then we're going to throw in whatever independent variables we want. So like one dependent variable, we can put in multiple independent variables. Now, when I do this, I can do multiple controls, and we call a variable of interest. A variable of interest in this case might be age. We think that age matters here. But I might also have control variables. And control variables are other things that I know matter, but I'm not really necessarily interested in. But I want to use them to isolate the effect of my independent variable of interest. So the idea here is that, and this is what makes multivariate regression so powerful, is that if I include multiple independent variables in the model, the estimated betas for each independent variable automatically hold constant the effects of all the other independent variables in the model. So if I include in my model age and political conservatism, people's political ideology, then the coefficient on age is going to be the coefficient on age holding constant political ideology. And the effective ideology will be the effective ideology holding constant age. And if I include multiple variables, it can scale up. So if I include age, political ideology, and gender, the coefficient for age will be the effect of age holding constant political ideology and gender. And same for all the other ones. So it allows me to statistically control for all the other variables that I include in my model. So if you ever hear someone talk about statistical controls, this is what they mean, that they're including these other variables in their regression. You include them all together, and you see whether this variable is significant, even controlling for these other variables. So the age effect, so if I think conservatism might be what's driving the effect of age on people using homosexuals, well, then let's see. If I throw age and conservatism in there, I'll see what effect of age remains after I control for the effect of conservatism. So when researchers are trying to understand the effect of one IV on a DV, they're generally going to need to include any other independent variables that are likely to have an effect. So the most commonly used variables are going to be, typically we're going to use gender. We think gender basically always matters. So we're going to use some measure of gender. Typically we're going to use someone's biological sex. It's imperfect, don't worry about it. So male or female. We might use a marker for class, that is something like education or income. And we might also use some sort of variable for race or ethnicity. Again, there's lots of different options there. But we're trying to use those as control variables because we know that gender, class, and race basically always matter. And so we want to control for them when we're isolating the effect of our independent variables of interest. Now, this does cause some problems, though. The big problem this causes, the big problem we have here is that many of our most common independent variables, like race or gender, wind up being nominal level variables. Remember, our order variables, we have nominal, ordinal, interval, or ratio, NOIR, NOIR, so nominal, ordinal, interval, ratio. And nominal variables are our lowest. So if I've got a race variable, there's not necessarily a number attached to it. I mean, I could add a number. I could say white is 1, African American is 2, Hispanic is 3, but there's no real value to that. There's no order to it. I just made up numbers. They're arbitrary. And so I can't really use nominal level variables in my model, in my regression. So the way we do this is by turning the nominal level variables into one or more dichotomous ordinal level variables. We're going to call these dummy variables. So a dichotomous ordinal level variable means it's going to have two values, 0 and 1. And those are going to be in any order. Now, it doesn't have to be 0 and 1. It can be 5 and 38.3. It doesn't matter. But the math works out a lot better if we make 0 and 1. So we know we're going to do that. So if I've got a nominal variable like gender, I've got male and female. So what I would typically do is I'd say, all right, male is 0, female is 1. So now I've got this male-female variable has turned into an ordinal variable. 0 is male, female is 1. So it's ordinal in that women are higher on the scale than men are, right? So I've got a variable that is now an ordinal level variable. And I can use that in my regression model because I can also interpret what the effects are. That is the effect of the coefficient. The coefficient is going to mean what is the effect of being female rather than being male. So when I've got nominal variables, I'm going to turn them into dummy variables. Now, how many dummy variables do I need? Well, if I've got, the general rule is you're going to need one fewer dummy variables than the number of categories that you want to represent. So in gender, I've got 2 categories I'm representing, male and female. I know the world's a lot more complicated than that, but most of our data is just so I have those in it, so we're going to deal with that for now. So I've got 2 categories, male and female. And so I'm going to need one fewer than that in terms of the number of variables I need. So 2 minus 1, I know we're doing tough math here, guys. 2 minus 1, I'm going to need one dummy variable. So I have a variable that represents whether someone's female rather than male. Now, why do I need 2? Well, if I have a variable that represents whether you're female or not, I don't need a separate variable representing whether male or not, because I'm assuming everyone who's not female is male. So I've already represented who the men are. I can figure it out by seeing the people who are 0 on my gender variable. If I've got more categories, so let's say, for instance, I've got a race variable, and I've divided the world up into 5 different racial categories. In this case, white, African American, Asian Pacific Islander, Hispanic, Latino, and other. So I've got 5 categories. How many dummy variables do I need? Well, I need 4. So I would create, if I want to represent all 5 categories, and you don't have to, you could represent a subset, but if I want to represent all 5 categories, I would have 4 different variables, right? So I'd have variable for white, African American, Asian Pacific Islander, and Hispanic. Note I don't have a category for other. Why not? I don't need a variable for them because I know who my other people are. So in this case, my white, I've got a variable for white. The white people get 1, everyone else gets 0. Variable for African Americans get 1, everyone else gets 0. Variable for Asian Pacific Islander, Asian Pacific Islanders get 1, everyone else gets 0. A variable for Hispanics get 1, everyone else gets 0. I already know who my other people are, the people in the other category, because they're the only people who got 0 on everything. So they got 0 on everything, as you can see going along the bottom here. So they get 0 on everything, and so therefore I've already identified them in my data. So I don't need to have a 5th dummy variable. I have to represent 5 categories, I would use 4 dummy variables. Now, I'll tell you, I wouldn't normally actually use all 4 dummy variables. Mostly, I would probably use 1 for African Americans, 1 for whites, and then throw everyone else in kind of the other category. You don't need to have all the variables, but you can if you want to. You have maximum number of dummy variables you can make. Have a nominal variable is equal to 1 less than the number of categories you're trying to represent. All right. This can get a little tricky to do in SPSS. This is covered in one of the other YouTube videos we have here already, one of the older YouTube videos. So it does get a little tricky, but you'll be able to figure it out. We use the transform recode in different variable option, and you should be able to figure that out pretty easily. So once we take a look at once we figure out all of the relevant independent variables, so for our regression, I'm going to assume we took all the dummy variables, all the nominal variables, control variables, and turned them into dummy variables, and we can then include them in our model. So in this case, let's go back and let's build our field thermometer homosexuals. And there's other things that I think are going to matter. So for instance, I know age, that's what I'm interested in. I want to see what the effective age is. But there's other things I might think matter. So your political views, so the Republican or Democrat. I might think that your education level matters, your income matters, your racial category matters. So I'm going to use in this case African American, Latino, Latina. Your gender matters, and your religious views matter. How often you attend, in this case, how often you attend religious services. So I'm going to throw all those independent variables into one model, and the results are going to be exactly the same as if we had just one variable at a time. So I throw all of them in at once, and I get this giant-ass regression table. Look at that. Ooh, huge. Now I'm going to ask you guys to go to the Blackboard page and open up the file is called Method Slides Chapter 13, so you can follow along with this. So we can take a look at this together, and we can go through it. Because I know you're looking at this as mirror image. That's no good. All right, so I want you to open up. It'll take a minute to open that up, the PowerPoint slides for Chapter 13. So I've got all my relevant independent variables in there. And what I want to do is try and figure out exactly which variables are significant and which ones aren't. Remember, and what the size of the effect is for each of them. Okay, so anyone having trouble getting that open? Hopefully, if you are, we'll give you another minute. So we're looking at our big old regression table here. And in this case, I've got 8 independent variables now and my constant. So it seems like that would be much harder, but actually exactly the same way we interpreted it with the univariate. So in this case, if I take a look at my top independent variables, so not the constant, but the first independent variable I've actually included in the model, I've got my age of respondent. So the age of my respondent, in this case, is a coefficient of -0.224. Now that's a little lower than my coefficient was before. If you remember, when I just included age and nothing else, my coefficient was -0.314. Now it's down to -0.224. What does that tell me? Well, what that essentially tells me is that some of the effect of age, some of the things that look to be the effect of age on my view of homosexuals was actually attributable to these other factors I've now included in my model. So if I don't include the other factors, it looks like every 1 year you get older, your view of homosexuals goes down by 0.314. But it turns out age is only responsible for 0.224 of that. And the 0.1 that's left over was responsible to these other factors. So age has some independent effect of these other factors, and also some effect that is contingent on these other factors. Make sense? All right, so age did have an effect of negative 0.314, a beta of negative 0.314. Now the beta is lower, it's negative 0.224. Okay, no, it's actually bigger, it's negative, don't worry about it. All right, so that means for every 1 point of increase in age, my expected value of views of homosexuals go down by 0.224 points. Now, is that significant? Well, if you take a look again at your regression output, the standard error is 0.060. So my first test for significant or not is if my beta is twice as big as my standard error. So my beta, negative 0.224, is that twice as big as 0.06. Yeah, 0.06 doubled is 0.12. And my beta is negative 0.224, twice as big as that. Just doing with absolute values, again, negative positives don't matter. All right, second way to find out if my age value is significant or not. Negative 0.37, my t-value. My t-value is negative 0.3717. Now, for a 95% confidence interval, two-tailed, my critical value is going to be 1.96. So if my t-value is an absolute value greater than 1.96, my coefficient is significant. In this case, my t-value is negative 0.3717. So therefore, absolute value is 3.7, bigger than 1.96. I'm good. It's significant. Finally, look at my significance row, significance column. This is the last column here, is 0.000. Well, my critical value for that is 0.05. Is that less than that? Yes, it is. So it's less than that. I have all three tests on the same thing. I did it right. And I get 0.0, I get a significant result. All right, let's go down one row to educational attainment. So my beta on educational attainment is 3.211. All right, so 3.211, that's my beta. My standard error is 0.662. Is that significant? Well, let's see. Is my beta twice as big as my standard error? Yeah, it looks to be about 5 times as big as my standard error. So that looks to be significant. I can confirm. Let's look at my t-value. T-value is 4.8, critical value of 1.96. So yes, it is significant. And finally, look at my significance value, 0.000, has to be less than 0.05. So again, three tests for significance, beta relative to the standard error, t-value, and significance. Pick whichever one works best for you. All right, let's do one that's a little bit trickier, right? Household income. In household income, my beta is 0.036. Now, what does that beta mean? Now, interpreting betas is pretty easy. Just remember it as a Mad Lib. You had Mad Libs when you were kids, right? So for interpret a beta, just remember the Mad Lib of it. A 1 point increase in X leads to a beta increase in Y. So in this case, a 1 point increase in household income, that's my X, leads to a beta 0.036 increase in Y, which in this case is views of homosexuals. So a 1 point increase in household income leads my beta, meaning my view of homosexuals, to go up by 0.036. We've got a problem. Is that significant or not? All right, so my value of 0.036, my beta is 0.036, my standard error is 0.182. Is that significant? Well, it doesn't look like it, right? Because twice my standard error is 0.36. That's much bigger than my beta of 0.036. If you'd like to confirm, let's look at my t-value. My t-value is 0.197. What's my critical value for t? Two-tailed, 95% confidence, 1.96. Less than that. It's not significant. And finally, my significance score. I'm looking for less than 0.05. In this case, I get a significance score of 0.844, way more than 0.05, so therefore not significant. All right, so here's what I want you guys to do now. Assuming you've got this open, I want you to take a look at the value for household income. So the effective household income, the beta is 0.03. I'm sorry, not household income. The beta for is respondent African American. The beta is negative 4.307. So what I want you to do is take a look. I'm going to give you 2 minutes to figure out if there's significant effect of being African American on your view of homosexuals. All right, take 2 minutes, figure it out. Those of you who might not have it open, I'll put it up here. So the t-value is 4.307 with a beta of 2.5 and standard error of standard error of 2.5, standard error of 2.5, a t-value of 1.719 or negative 1.719, instance value of 0.086. Just take a look at that and figure out if this is significant or not. I'm giving you 2 minutes. I'll leave that up so in case you need it. So figure out if this is significant or not, and whether this is significant, whether it's significant effect of being being African American on your view of homosexuals, controlling for all these other factors. I know it's reversed. I know. I have not figured out how to fix that. I'm sure there's some option here to like mirror image it. But come on, guys, I feel like I'm doing pretty well just being able to live stream stuff on YouTube. I feel like I'm a technological wizard right now for being able to figure this out. So these are worried about getting individual help in the lab. We should have a lab. We should have some time in the lab next week. In addition, I'll be running at least 1, maybe 2 lab sessions during your reading, in the run up to finals week to help you guys out with any problems you might be having. Honestly, the sickness came out at the worst possible time for you guys because we're getting difficult stuff. Apologies for it. Don't worry, we'll make it up. All right, so who's going to hit me with their answers about whether there is a significant effect of being African American on your view of homosexuals? So I'll give you a few seconds for someone to put in their answer. If you don't, I will start calling you out by name. I'm not seeing it. All right, Cecilia, help me out. Cecilia, is it significant or not, and how would you know? Give me one way of knowing whether it's significant or not, and one way to know if it's significant or not for the coefficient of African American. Cecilia, calling you out. Hit me. So I'm waiting for Cecilia. While waiting on Cecilia, I also want to hear from, let's see what we got here. I want to hear from Luis. And I want to hear from, let's see, Stephanie. So I want to hear from Luis and Stephanie also. Remember, there's 3 ways of knowing if something's significant or not. So we're waiting for Cecilia, Luis, and Stephanie to tell me if that coefficient for is respondent African American, tell me if that one is significant or not. So Cecilia, Luis, and Stephanie, help me out. I mean, don't help me out. I already know what's going on. But I want to make sure that you understand exactly how to determine if something's significant or not. If you don't, if you have a question about it, let me know. I am marking this down as participation. So if you're not able to answer or you don't put anything in the chat window, then you'll be marked down for that. So I'm waiting for Cecilia, Luis, and Stephanie. Hey, there we go. So beta divided by standard error is beta twice as big. So is the relationship significant or not? So that's what I know. So the beta in this case is negative 4.307. The standard error is 2.5. Is that significant or not? To commit. Well, all right. So the beta divided by standard error. So it's 4.3 and 2.5. Well, no, you said yes. It's not. It's not actually. Why? 2.5. We double. It's 5. That's a little bit bigger. So the beta is not quite. It's just outside of it. So it looks like it's close to significant, but there's no such thing as close to significant. Either significant or not. So it'd be non-significant. Almost exactly. Almost, but almost doesn't count as we're talking significance. All right. Do I have a second way of doing this? Denisha did the hard one, so there's easier ways. All right, so I'm marking down Cecilia and Luis. Significance column. Yeah, that works. Significance column in this case is 0.086. My critical value is 0.05. Stephanie, all right. Would it not be significant because the significance is bigger than 0.05? So Stephanie, you're absolutely right. Significance is bigger than 0.05. I need smaller than 0.05, so it is not significant. And Liam says you can use the t-value. Absolutely. In this case, my t-value is negative 1.719. Is that significant? What value do I need to be significant? Not 1.719. Does that work? Well, this is an easy one at this point because remember, all three tests tell you the same thing. So the t-value is negative 1.719. I'm looking for a 1.96. Absolutely 1.96. Doesn't get there. So it's not significant. So there is no significant relationship between being African American and your view of homosexuals. Yes. Okay, so there's no significant relationship there. Now, there's not. If we just did one variable at a time, it's possible there would be. But when we control for everything else, Ty, does the t-value always have to be above 1.96? It depends on positive or negative. The absolute value of t always has to be above 1.96. So if it's negative, it has to be less than negative 1.96. If it's positive, it has to be above 1.96. So if we went to the next one, for the effect of being female, we see the beta is 11, standard error is 1.8. Definitely significant, more than twice as big. Confirm that t-value is 6, and the t-value of 6 is way more than 1.96. So definitely significant, and a significant score of 0.0000, so less than 0.05. Okay, so all these tests are going to tell us the same thing. Now, what I want to do, so let's do one more with this. Let's take a look at how often people attend religious services. So how often attend religious services, the beta is 2.666. And I want someone to chime in and tell me whether it's significant or not and what test to use to determine if that is significant or not. So someone hasn't chimed in yet. Tell me whether that is really attending religious services is significant effect or not, and how you know if it has a significant effect. So it gets hot here in my office. It's a small room, so the heater makes it really hot in here, so I drink lots of water. Also wearing a sweater. I shouldn't be wearing a sweater. It's hot in here. What am I doing? I'm not going to take my sweater off in front of you. Christopher says significant because it's more than double standard error. Yes, absolutely. Standard error is only 0.773. Stephanie, significant, but got to tell me how you know, Stephanie. Come on. Yeah, so it does need to be significant. So Nisha said, yeah, t-value, yeah. Yeah, so you're looking for an absolute value of 1.96. Absolutely right, Tanisha. So in this case, yeah, you guys are doing the hard one first, the beta over standard error ratio. That's the hard one. Again, t-value for me is always the easiest. In this case, t-value is 3.447. Oh, Cecilia. Student that doesn't get actually you do first. Okay, well, sorry about that. All right. Yeah, good job, guys. Good job, folks. Right? So yeah, you guys are doing the standard error one. You can do that. Again, that's the hard one, I think, because you actually have to divide. If you want to know what the ratio is, just look at the t-value. T-value tells us the exact same thing. In this case, 3.447. Double 3.47 is bigger than 1.96. You're good. We know that one is in fact significant. Now, let's move on and let's make this a little more difficult. What does that beta coefficient actually mean? So let's go back to the one for African American. The beta coefficient on African American is negative 4.307. Now, African American, that's race, so it's a dummy variable, right? So you have to pay attention to how it's coded. So for the African American variable, it is 0 if you are not African American and 1 if you are African American. Now, in a dummy variables are always going to be interpreted relative to the excluded category. So let's skip to African American for a moment. Let's go to female. The beta on female is 11.066. Ty asks, when you say the t-value, do you mean what is found from the z-score? No, the t-value is just the column that is the t. It'll say, so the t-value is actually just the beta divided by the standard error, gives you the t. And that's reported in it's reported in one of the columns. This column over here in your regression output just gives you the t-value. Okay, so let's take a look at female. So female has a coefficient of 11.066. What does that mean? So the coefficient of 11.066 means that if you go up by 1 point on the female variable, remember our Mad Lib, if you go if you go up by 1 point on X, Y increases by beta. So up by 1 point on X, 1 point on X, 0 is female, 0 is male, 1 is female. So an increase of 1 point means you're female rather than male. Your dependent variable goes up by 11.066. So that coefficient on female tells us that women on average have a value on the homosexual feeling thermometer of 11 points higher. So women on average are 11 points higher on the homosexual feeling thermometer than men are, and that is a significant relationship. We already know why it's significant. Now, it gets a little trickier when we're dealing with other sorts of dummy variables. With female, male, there's only 2 categories. But when we're doing other things like our race variables, it gets a little trickier. So we're interpreting the beta coefficient for variables where there's multiple dummy variables. So in this case, I've got race. If you look at our regression, I've got race is 2 different variables. I've got African American and I've got Latino Latina. And I know technically Latino Latina is actually an ethnicity variable rather than a race variable. I know, we're just doing the way we got here though. So if someone is Latino Latina or African American, those are the categories I have. So my excluded category is everyone who is not African American or Latino. Okay, so that includes white, Asian Pacific Islander, and other. So all those other categories are the baseline category. So my baseline category is white, Asian Pacific Islander, and other. So my African American coefficient tells me that African Americans on average are 4.3 points lower on the dependent variable than people in the excluded category, the baseline category of whites, others, and Asians. So African Americans are on average 4.3 points lower because I've got that beta coefficient of 4.3. Now, it's not a significant difference. So I would be perfectly right to say there's no significant difference between African Americans in the baseline category in how they view homosexuals. Now, the coding of these variables also can matter a lot because some of these variables are not coded the way we would want them to be. So, for instance, the religious services variable looks pretty weird because if you had to guess, right, do people go to church more often? People go to church a lot. Do they like homosexuals more or like homosexuals less? Do more religious people like homosexuals more or less than less religious people? And in general, we would think that people who go to church more are going to have more negative views of homosexuals because, the Bible isn't so great on homosexuals. It's a whole deal. So if that's the case, why is it that I'm getting a positive coefficient? So it looks like the more you attend religious services, the coefficient is 2.66. So people who attend religious services more like homosexuals more. Now, why does it seem that way? It seems that way because of the way the variable is coded. We have to pay very careful attention to the coding of the variables. The religious services variable is coded in a weird way. It's coded such that the higher your value on that variable, the less you go to church. So the higher value, so people who are higher on the religious services variable are actually going to church less. Now, there's a good reason why they write the variable that way. Because they think it's more socially desirable to go to church more than go to church less. They put the socially desirable ones at the top of the scale, so people pick those. But it just raises the point that we have to pay very careful attention to how the variables are coded. If we didn't pay attention to it, we think, oh, people go to church more, like homosexuals more. But it's in fact the opposite. And we could change the sign of any of these coefficients just by changing the way the independent variable is ordered. So whenever I give you any activity having to do with regressions, I'm going to tell you how all the variables are coded. And that's going to be very, very important because it's going to tell you how you have to interpret those variables. So you have to interpret it relative to how the variable is coded. If the variable is coded such that higher values mean that someone does not go to church very much, we have to take that into account when we interpret what the beta coefficient means. All right, so just one more thing on interpretation. Look at the coefficient on educational attainment. The coefficient is 3.2. What does that mean? Essentially, it means every 1 point increase in educational attainment, as you get more education, you like homosexuals 3.2 points more. Okay? So, what do you have to take away from these regressions? A couple things. Number one, the coefficient, the beta, the slope, for any individual independent variable in my model automatically accounts for all of the other variables included in the model. Meaning that when I take a look at the effect of age, that's automatically accounting for all the other independent variables I include in this model, like political views, like gender, like how often they go to church. I've automatically I've automatically controlled for all of those things. So it's telling me what the effect is of age, holding constant all of these other factors. So the more control variables I include, essentially the more confident I can be in my results. Second, when I'm interpreting the coefficient, remember your Mad Lib. A 1 point increase in, insert x here, leads to a beta increase in y. So in this case, for educational attainment, a 1 point increase in educational attainment leads to a 3.21 point increase in views of homosexuals, right? So when interpreting the coefficients, just remember the Mad Lib. A 1 point increase in x leads to a beta point increase in y. Finally, we have to determine whether these relationships between the independent variables and the dependent variable are actually significant, controlling for all these other variables we've included in the model. So how do we know if it's significant? Again, we've got 3 ways of doing it. So I've got 3 ways of doing it. I can take a look at the ratio of beta standard error, see if beta is twice beta standard error. I take a look at the t-value, see if the t-value is an absolute value greater than 1.96, or the significance value, see if the significance value is less than 0.05. Now, also, when we look at the regression as a whole, we can interpret the R squared, also called the coefficient of determination. So the higher the R squared is, the more of the dependent variable we've explained with the independent variables in our model. Remember, we just included age. We explained 3.6% of the variance in our dependent variable. When we included all of these variables, our R squared now goes up to 0.139. What does that 0.139 mean? That means I've explained 13.9% of the variance in my dependent variable with these variables. So 13.9% of my dependent variables explained by the age of the respondent, their educational attainment, their household income, their race, their gender, their party ID, and how often they go to church. 13.9% is explained by that, meaning that 86.1% is still explained by other factors or random chance. That said, in social science, 13.9% is actually pretty respectable. Your R squared is going to be bounded. It's a percentage, so it's going to be bounded by 0 and 1. The minimum is 0, the maximum is 1. You'll note in this case, our adjusted R squared is 0.130. So our R squared is 0.139 with an adjusted R squared 0.130. So remember, the adjusted R squared gives us a penalty for every variable we include. So if we include a lot of useless variables, our adjusted R squared is going to be lower, significantly lower than our regular R squared. So if we, so in this case, we can see our adjusted R squared isn't much lower, so all our variables seem to be doing a pretty good job. In fact, if you look at our model, we only have 2 variables, income and African American, being African American or not, that have a different, they have a non-significant effect. So when we take a look at our model, we can also then use this to build an effect, to build an expected value. Oh, the critical value is significant for R squared. There is no such thing. So Cecilia, there's no such thing as a significant value for R squared. It just isn't. So R squared is the coefficient of determination, tells you how much you've explained. You know, if you've got a very low R squared, it means you haven't explained very much. You should probably add some more variables. If you've got a very high R squared, it means you probably messed up and added some variables you shouldn't have added in there. So if you're, as long as your R squared is more than about 5%, you're probably okay. If it's more than about 75%, you probably messed up somewhere. So a low R squared, all that means is there's a lot, it could be there's a lot of error in the model. People, I think, actually pay too much attention to R squared. It's not telling you what people want to think it's telling you. Okay, so if I take a look at all of my variables put together, I can actually build an expected value in the same way that I built it for any particular one variable, if we just had age. I can build an expected value for all of my variables together. So when I do that, I'm going to follow the exact same equation. If you remember, my y hat, my equation for my expected value, is just going to be y hat equals beta 1x1 plus beta 2x2 plus beta 3x3, all that, plus c. And I can do that whole thing for all of my variables. So if in this case, beta 1 would be my first independent variable. X1 would be whatever value of x I have for that. So in the equation, so in the regression we just ran, my beta 1 is age of respondent. So beta 1 in this case is negative 0.224. Then, so if I want to figure out my value of y, I would take beta 1, negative 0.224, times whatever value I have for age. Now, when I'm asking you to do this, I'm going to give you a value. Say, okay, give me a 40-year-old male. So you put a value of 40 in for the age. 40 times 2.24. Then a value for the next variable, which is educational attainment. So they might have a value of 5. And again, you're going to get all of this from the data set. It'll tell you what values are reasonable for that. So we 5 times, in this case, 3.211. Then household income. Household income might be a value of 20. So we plus 20 times 0.036. And we'd have a x value for each one of the independent variables. Multiply each of those x values times the corresponding beta value and add them all up. Then finally, add in the beta for the constant, and then that'll give you an expected value of y. So to find an expected value for given all these independent variables, all we do is plug in an x value. And again, x value is not going to be, it's not obvious what it is. Sometimes I'm going to give you the value. Other times I'll say just use a mean value and go up or down 1 standard deviation. So if I just use mean values, mean value of age in this is like 45, educational attainment is like 7, income is like 19. So I plug in all those mean values. As I plug in all the mean values, multiply each value I plug in for the x times its own beta, and then sum up all the results and add in my constant. When I do all that, I'm going to get a value. So, for instance, if I take a 40-year-old white person, so they've got a value of 0 in African American Latina. Say the Republicans, they've got party ID of 6. They're a woman, so female is 1. They've got a bachelor's degree, so education is 6. And a mean household income 11. He goes to church every single week. I just plug all the numbers in. Each beta gets multiplied by the value of x I've assigned to it, and add them all up, add in the constant, and I'll get a number. So, and that will tell me what I would expect that person to have for their view of homosexuals. Now, the math here is very easy. The thing people get hung up on here is what value they're supposed to put in for the x. Remember, your y hat is going to equal beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. So you have to have an x value for every one, even the ones that are not significant. Remember, even the variables that are not significant still matter, because all of my independent variables are still controlling for the effects of the other variables, even if those variables are not significant. So I have to include all the variables in the model, even if they are not significant, when I'm doing my expected values. So my expected value is just going to be my y hat is equal to beta 1 x1. So beta 1 comes from regression output, right? Beta is just that first column right there, my beta, times whatever value I've assigned to my x value, age, education, time, whatever. So beta 1 times x1, and then I add in beta 2 times x2. And then I keep on adding it in, every beta times an x, until I get through all of the variables, whether they're significant or not. And at the end, I go ahead and throw in my constant. Do all that, and I will get a value on the expected value of my dependent variable for any particular value of my independent variable. So Allison's asking, are we going to be going over finding these values of data in the lab? Finding these values or data. Well, finding the values is pretty easy, right? So finding the values for the beta that's just that's in the regression output. So we'll do that in the lab. I'm going to be assigning you at the end of this. I'm going to be assigning you a couple worksheets that you can do to work on this to make sure you've mastered it. So that should help you out and give some practice there. All right, so we've got the basics. We've got just a couple more things to learn before we apply it. We're going to have to do some interaction effects, and once we do that, we're all good. We'll save that for when we're actually in the lab, though, so you guys can do that hands-on. So what I'm going to do now is I'm going to be putting some worksheets up on the Blackboard site, and I want you to do those worksheets on your own and let me know if you have any problems with them. Now, it's important you actually do them and you actually figure out, okay, what part of this do I not understand? Because I need you to bring those questions, the stuff you didn't understand, with you to class next week. Now, don't just tell me I don't understand any of this, because that's not exactly useful. but you have to tell me which part of this you're not quite getting. Alice asking, when will I post the homework? I'll be posting it in about 5 minutes, I promise. So you have to come with your questions, stuff you did not understand. If you guys want to work together on it, fine with me. Because I won't be grading these homeworks. These will be something I want you to do on your own to make sure you understand it. If you don't understand it, it's going to make your life a little bit harder when you get to the final exam. So I'm going to shut off the live stream now. If you've got any questions, you can email me, or actually I'll keep the live stream going on for another 5 or 6 minutes. If you guys have any particular questions you want to ask, and then I'll be posting up the Blackboard page. Christopher's asking, will you offering office hours before the final is due? Yes, absolutely. Okay, Dee's asking, well, if I didn't understand this in the last homework, but now I do. Well, you want to resubmit it? Go ahead. I probably haven't gotten a grading yet. Good, resubmit it. Just let me know this is the new version of it, and now you understand it. That's fine. So yes, it will be holding office hours, and we'll be holding extra. Well, I'm glad Christopher's saying the same thing, that they now understand stuff. Well, good. So resubmit it. Is our final due on the 19th? Check your syllabus. That sounds about right. Sounds good. But yes, I'll be holding extra office hours. The plan is, at this point, I'll talk to the cardiologist tomorrow and get the all clear to come back. Actually, the big problem right now is driving. I'm still not allowed to drive yet. So the plan is for me to be back on campus perhaps as early as Friday, but certainly by the middle of next week. Next week for our regular class, we'll be meeting in our regular room and then going up to the computer lab because we'll talk about some stuff before we get to the computer lab. Then I think next week is officially our last class, which is kind of terrifying. But we'll be holding at least 1 and probably 2 sessions in the lab to help you folks out with additional help that you might need to get all this done. Okay, again, more questions. I'm happy to deal with any more questions that you guys have. If you don't have questions, you don't care about a response to the questions. Silly's asking, trouble with t-tests and the homework activities from last week. We'll bring those to class next week. Yes, you can bring those to class. I'll be happy to explain those t-tests. If we're being totally honest, that's just not on your final. So you can probably, as long as you understand the basis of it and how t-tests and z-tests apply to regression, you can probably leave that aside. As long as you can build a margin of error, I'm probably pretty good. So you're going to bring this class? Yeah, bring whatever questions you have to class next week. Absolutely. You're welcome. Yeah, no, look, guys, I know that doing this on your own is hard. I know it, and I apologize for that. Basically unavoidable. I looked into getting a substitute, but I worry that would have just confused you more. So hopefully the live stream helps out with this. It seems like some people learned some, figure out how to do some stuff. And once we're in the lab, it's going to be a lot easier. Some of you, again, I know have already figured this stuff out, and it's easy to you. Others haven't figured it out yet. So look, help each other, and I'll be here to help you out. I'll be asking if you did this the last time, we can bring it next week, because now I think I do. Yes. Do it. Now, who already understands it? Yeah, I have to go back to my grading and figure out exactly who's getting this perfectly. But I know I looked at some of it, and some of it was already done perfectly. So I will be, like I said, once we're done with the live stream, I will be posting everything on the regression, all the regression activities on the Blackboard page for you guys to do by yourself or with friends, however you want to do it, so that you can make sure you understand it and bring any questions you have about how to do that with your class. My normal pattern is I go around and tell you why you did something wrong. I'll be a little more generous this time, I promise, and just tell you, what you got right. And I'll try to be nicer about it. I'm just trying to be less stressful and nicer in general. All right. With that demand for the names of people who are already doing well on it, we're going to leave this aside. Thank you very much. And as I said, I will be posting your stuff on Blackboard momentarily. All right. Thank you very much, and I will see you next week.